Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking at Chapter 7, Equations of State, and we will be looking at the virial equation of state in this lesson. So the virial equation is an equation that is based on modeling chemicals at the microscopic level, looking at how the molecules move around in a mixture with others. It is based on quantum chemistry and statistical mechanics. Quantum chemistry uses quantum mechanics to build very detailed mathematical models of the atoms and molecules, and MECH is going to apply probability theory to the modeling of our thermodynamic systems. Now, the virial equation of state is very simply infinite sum of 1 over v to increasing powers, okay? So z is equal to pv over rt plus, which is equal to 1 plus b over v plus c over v squared and d over v cubed and as many other terms as you are interested in. The 1, the first term there, represents ideal gas behavior. So each of the other terms are going to basically be modeling deviations from ideal gas behavior. If we truncated it there, then we'd say that we thought it was an ideal gas. Each additional term is going to cause an improvement. And those changes, those modifications, are based on intermolecular interactions that are causing those changes. Remember our assumptions for an ideal gas. The molecule's small, it's round, and it doesn't ever encounter another molecule. So when they actually do interact, what is going to happen? How frequently are these things going to interact? That's going to determine the coefficients B, C, D, etc. The frequency of a specific molecule colliding with another molecule is going to depend on the molar density. Okay, so how close together are those molecules? Since the volume is volume per unit mole, 1 over volume is a molar density. So we could say that Z is 1 plus B times the molar density plus C times the density squared plus D times the density cubed, etc. But that density is going to really be a good predictor of how frequently the molecules bump into one another. So that 1 over V is going to be proportional to the frequency of any two molecules colliding, and B, the coefficient, is going to represent the effect of those intermolecular interactions on the Z value. So the frequency is the 1 over V. The magnitude of that interaction is going to be the B, and that will vary, but depending on the substance. C over V squared is going to be quite similar. It's going to represent the effect of 3 molecules interacting. D is going to represent 4, and so forth. So the book has, and I'm going to really go through these quickly. I recommend reading the book if you're interested in this, and we will be doing more of this when you take your Thermo 2 course. But statistical mechanics, very briefly, is looking at, and we'll just look at here for the sake of simplicity, 3 different molecules that are in a vessel, okay? The entire vessel only has these 3 molecules in them. They could be arranged all sorts of different ways, right? So if you look at these pictures here, this molecule, the other 2 are kind of near it. Here, the other 2 molecules are farther away, but they can be arranged in any number of locations and distances from each other. We talk about a radial distribution function that describes how far away each molecule is. Now, this drawing that you can't see, under here, is if this is my molecule, they go radial lengths away from it, and so they measure things in terms of radial distances. So if we have this molecule here, some molecules are 2r away, meaning that the radius to the radius of the other one, there are 2 radius lengths, or a diameter, okay, between the center of this molecule and the center of this one. But for this molecule, it's 2 times the square root of 2r. This is closely packed. And this one, it's 1, 2, 3, 4 radial lengths distance between them. And so for any point, you can use geometry and you can estimate what the radial distance is in terms of radius of the molecule. And then for our packing, we say, okay, well, I have 1, 2, 3, 4 of those that are at a distance of 2r. And the distance 2 square root of 2r, I have 1, 2, 3, 4 of those, and so forth. And you can go through and mark those in, and that gives us a radial distribution function of our starting mixture. But if we allow things to move, then that's going to change over time. And so we add the statistical chance that different molecules will be at different positions. So we can do modeling where we run these many time steps forward and watch what happens as the molecules move around and find out the different radial distances from the center of each molecule. And we do that, and we can come up with radial distribution functions for our spheres. And that's what these Lennard-Jones potential plots are that you see here. And again, I'll let you read more about that in the book, but that's the gist of what the statistical mechanics is doing for us. So it's looking at simulations and then what are the likelihoods, the probabilities that molecules will be located at various positions within the space. So the virial equation, returning to that, for very low pressures, when you have a very large volume, okay, very small density, the equation is going to simplify to being an ideal gas, okay, Z equals 1. But as the pressure increases, you get a large V. It's not huge, though, okay? At that point, then probably we can approximate with only these, and we can assume that these additional terms are very close to 0. And as the pressure increases, we will need to add more and more terms. Most of the time, we stop with the first. So this is the virial equation as it's typically used. This equation, however, is a little bit different. Instead of saying 1 over V, it's written in terms of P and T. Now this B is different inherently from the other one because V is not equal to RT over P. That would only be true if it were an ideal gas. So Z is 1 plus B prime times P over RT, okay? We can reconcile these using some mathematical relations, of course. Generalized correlations are one way that we can estimate those. And so this B prime PC over RTC is equal to B naught plus omega B1, where B naught is 0.083 minus 0.422 over TR to the 1.6 power. Remember, TR is T over TC. And B1 is 0.139 minus 0.172 over TR to the 4.2 power. These expressions are pretty simple to use, and we have something that mathematically is not particularly challenging. If we do these using these correlations with the Pitzer-eccentric factor, then we can also add in the C term. written here. C naught is 0.0147 plus 0.02432 over TR minus 0.00313 over TR to the 10.5 power, and C1 is negative 0.02676 plus 0.05539 over TR to the 2.7 minus 0.00242 TR to the 10.5. Okay, we could continue with this if we wanted to. Generally, the B only is necessary when the pressure is below 5 bar. From 5 bar and up, probably you want to add the C terms in there, okay? But so these are our approximations using the virial equation for a pure substance. We had earlier looked at an example for butane using the graphs for the estimate of Z. We now can do this using the virial estimates, and we'll do this for B only. No reason to make ourselves crazy on this. In this case, TR is 0.9, PR is 0.263, and we can then calculate B naught and B1. Using the formulas from the previous slide, B naught is negative 0.4165, and B1 is negative 0.1287. So B times PC over RTC is B naught plus omega B1, and that is negative 0.4422. Therefore, Z would be 0 plus negative 0.4422 times PR, which, okay, so 1 minus 0.4422 times 0.263 over 0.9 is 0.8708. This is not too far off for what I got when I was using graphical techniques. And so this is yet another way of doing this. We next need to look at how do I decide which of these equations to use when? And so that will be our next lesson. Thank you very much for your time.